Hello everyone, welcome again in Eng-Man YouTube channel. In this video, we will learn how to model a horizontal oil well with multi-stage fracturing. We will do the analysis and the modeling within WellFlo software. So we have learned many things in PipeSim and Prosper. Both of them are well modeling software, and WellFlo also is a well modeling software. It's also very useful. It's quite popular, and yeah, today we will learn with this software. Okay, this is the window of WellFlo, but before we do the modeling, we will talk a little bit about a horizontal well with multi-stage fracturing. So this is the idealized multi-stage fracturing in horizontal well. You can see this picture with the source given below. All right, this is the well bore. All right, this is the horizontal lateral section. This horizontal section, we call it horizontal lateral section. This symbolizes the fracture. Each icon shows a stage. So we have 4 stages of fracturing: first stage, second stage, third stage, and fourth stage. Or the other way around: first stage, second stage, third stage, and the last stage, the fourth stage. This shows the fracture width, all right, the opening, the width of the fracture, and the space between each stage. We call it fracture spacing. This is, of course, the stimulated volume, the volume between each fracture. And then this is the fracture length. This one, fracture length. And of course, this is the fracture height. All right, this fracture dimension will determine the performance or the conductivity of our fractures. And of course, it will influence or determine the productivity of our horizontal well. So that's quite simple. Now we can go back to our WellFlo software. All right, this is the window or the dashboard of our WellFlo software. You can see this picture shows our well. This shows the surface facility, the spirator, and this is the reservoir. This is the dashboard, so you can see a lot of parameters here for the fluid properties, the wellbore configuration, and reservoir, and also for the flow line. Now let's input our data into the software. First, initialization, general data. Yeah, you can input your general data like company, field, well, location, platform, the analyst, objective, and the nodes. All right, let's say we want to write multi-stage fracturing in horizontal well. All right, and then we click forward, or you can also click each section. Let's go forward or apply and then forward. Now we go to well and flow type. Of course, for the well type, we select producer without artificial lift. So in this video, we will not learn about artificial lift within the well. Flow type in the tubing, fluid type black oil, and the well orientation, we can select vertical, horizontal, or multifrac. In this case, we will select multifrac. Interesting. Apply, forward. Now we will select the flow correlations. For the well correlation, we will select Hagedorn and Brown standard equation or correlation. Okay, and well and riser L factor 1. And the other, we can leave as per default because we will not do downcomer or pipeline here. We will concentrate only within the wellbore. We can then apply and forward. Reference depths. Well type onshore, and the zero depth will be at Kelly bushing at 20 feet. The Kelly bushing to wellhead distance. All right. Again, apply and forward. Now we will input our fluid properties. PVT calculation method, black oil, and then you can follow my data. Oil API gravity 35. All right, the oil specific gravity will be calculated based on the oil API gravity. Gas specific gravity 0.65. Water salinity 30,000 ppm, and water gravity will be calculated. We will select the correlations for bubble point, solution GOR, and BO using Glasso. For the oil viscosity, BL correlation. And then for the gas viscosity, CAR, and surface tension, basic. We don't have inorganics in our fluid system, so we can input 0 or leave it as it is. And also for the PVT data calculator, for the properties in pressure, 6,000 psia, temperature 196, with produced GOR of 500 standard cubic feet per stock tank barrel. And then we can calculate. Yeah, this is the calculated parameters for the bubble point. You can see oil formation volume factor, oil viscosity, and so on and so forth. All right, so far so good. Apply. Yeah, you can see here the symbol turn from X to V like this. We go forward. All right, now we are in reservoir layers data. We go to general first. Name, let's say reservoir. Okay, we should be careful here. Reservoir pressure, 6,000 psia. Reservoir temperature, 196 Fahrenheit. Mid-perf depth, the depth of our mid perforation, 12,000. Okay, with reservoir permeability quite small, only 1.5. That's why we will do multi-stage fracturing, right? The reservoir thickness in TVD, 100 feet. Wellbore radius, 0.42 feet. And with water cut quite small, 0.15. In fraction, gas oil ratio, SB4, 500 standard cubic feet per stock tank barrel. For the IPR, we will generate the IPR using Vogel model. All right. With skin options and multi-frac horizontal well unchecked like this. Apply. All right. Later on, this section, the productivity index and absolute open flow will be calculated by the software. First, we go to the drainage area geometry. Okay, you can follow my data, but of course, later on in your real case, you should input as per your real configuration or real characteristics or your real data. Okay. Coupled radial and linear flow, of course, because we will have fractures here. So we will have radial flow and linear flow. Equivalent drainage radius, 912.10 feet, with drainage area will be calculated. Okay. Or in my case, I will input my drainage area. You can follow my number. Okay. Square foot with the DH shape factor will be calculated. And then the IPR, not yet generated. We go to relative permeability section. Yeah, you can leave it as it is as per default, but in my case, I will do a little bit modification for the numbers. First, in gas water endpoint parameters, gas relative permeability the same, initial water saturation the same, M 3.5. All right, water relative permeability 0.5, residual gas saturation 0.3, and 2. Okay, for the gas oil endpoint parameters, the same. This will be 1.7. For the KRG, 0.85, 0.15, 2.4. All right, and then for the oil water endpoint parameters, 1.25, 3.5, and then this one the same, and this one too. Apply. Okay. After clicking this one, plot, our relative permeability will be changed as per our data input. We can now go to multifract section. It is a very important section, so let's be careful. Horizontal lateral length, 3,000 feet. This will be the stages for our fractures. We will have 4 stages of fracture. All right. The first stage, the top MD, 7,500. Measured depth in feet. And for the second one, 8,200. Third stage, 9,100. And for the last stage, at 10,000. And also we need to input our fracture properties in each section. So we can now open. Okay. In the first stage, we will have 2 fractures. So click this one again. Okay, let's check. We need to input our fracture spacing, fracture width, fracture half length, fracture height, near wellbore fracture permeability, near wellbore fracture width, fracture permeability, and measured skin. So after you design your fracture, maybe within Fracate or SteamPlan or any other software to design hydraulic fracture, after getting the dimension or the geometry for the fractures, you need to input the information here in each cell here. In my case, I've prepared my data, so you can follow my number. All right. I will just input my number here. Okay, the same. Fracture height, near wellbore fracture permeability, 55,000 millidarcies. So it should be a big number. Fracture width, okay. Fracture permeability in my case will be 60,000. Measured skin 1. Apply. Okay. So you can see the length and number of fractures will be inputted automatically. You can check again. All right. Yeah, I can copy to input my second stage. I will have 2 fractures, paste, and then modify 400 and 400. Fracture width the same, fracture half length the same, fracture height the same, fracture permeability also the same, measured skin 1. All right, copy again. apply. Okay. Check again. Still okay. For the third stage, we will have 3 fractures. Okay. The fracture spacing 400 and then 200. Lastly, 300. The same 0.02 with half length. Need to modify 300, 325, 300 again. Fracture height, all the same, 200, all the same, 55,000. All the same for the fracture permeability, 60,000. Measured skin, yeah, you can input 0 or any other number as per your study or statistics. Apply. All right, the warning is incomplete data to perform calculations. Check all error messages. Okay. For the last stage, 10,000. Open the fracture properties. All right. We only have one fracture. Delete. Fracture spacing 300, 0.02. All right. And then for the fracture half length, 300. The height will be 200, 55,000, 0.01. Okay. 60,000. Measured skin 1. Apply. All right. Okay, now we need to input it again. 10,000. Apply. All right, now you can see here the productivity index is calculated. So our PI or productivity index is quite small, 0.1455 stock tank barrel per day per PSI with absolute open flow or AOF 690 stock tank barrel per day. You can also check the IPR, right? This is the IPR, the same for the PI and absolute open flow. All right. So it's very interesting. We input our reservoir data like this one, pressure, temperature, permeability, and so on and so forth. Drainage area geometry also for the drainage radius and drainage area. Okay, of course, because we will have radial and linear flow, because we have fractures, our drainage area will not be purely radial. All right. That's why we prefer to calculate the shape factor. Again, the IPR, the relative permeability, and the multifract properties. Okay, you can see the symbol for the reservoir. We are okay. So now we go to wellbore. First, deviation. This is the window for wellbore deviation. Data type, MD TVD angle. Enter data. We will input data for MD, measured depth, and TVD, true vertical depth. We need to input our data in this section. So click Add Row. I've prepared my deviation survey. I can copy and paste the data here. All right, this is my data. My well will be vertical from 0 to 5,000. And after that, it will have horizontal section down to 12,000 for the measured depth. This is the plot through vertical depth against cumulative displacement. Okay, it's very interesting. So this will be our horizontal section. Apply. We are okay. And of course, we need to input our equipment data. This is the window. First, we need to input our tubing. At row, okay, we name it tubing. Also, we can save our model. It's okay, save. Start point from 20 feet, all right? Because you can check again in reference depth. Kelly bushing to wellhead is 20 feet. So in equipment, starting point for our tubing will be 20. And then for the end point, 7,500. Okay, the segment length will be calculated. External diameter, 3.5 inch with internal diameter of 2,992 inch. Absolute roughness as per default. Flow configuration, of course, tubing with no drift diameter. All right, apply. And then we go to casing. Okay, add 2 rows. Okay, first casing, casing 1, the first section, and for the second one, casing 2. All right, the first section will be starting from 20 feet down to 7,500. All right, the same with our tubing, and then it will continue starting from 7,500 down to, of course, 12,000 MD. The external diameter, 7 inch. Internal diameter, 6 point, okay. Yeah, the same with absolute roughness as per default. Apply. All right, after that, we will input our temperature model within the surface data. Go to temperature. Okay, manual input. At row, I've prepared my temperature data. Copy and paste here. All right, so this is my temperature survey data. Apply. Okay, we have inputted everything. We can check again. General data, okay. Horizontal well with multi-stage fracturing. All right. Well and flow type, producer, tubing, and multifrac. Flow correlations, reference depths, fluid parameters. Okay. Check again. Calculate. All right. Of course, before running the nodal analysis, we better do the QA/QC, quality assessment and quality control, to make sure there will be no problem during the nodal analysis. Forward. So far, so good for the reservoir section. With deviation, equipment, for tubing and casing, we don't have restrictions. Temperature model. We go to dashboard. All right, so this is the dashboard. It shows the major parameters within its configuration. You can see here the productivity index 0.1455, total Darcy skin 1, and absolute open flow 690 stocks and barrel per day. All right. We will not do tuning here. This will be also a very interesting topic. Now we go to analysis. All right. We will do the nodal analysis within this analysis section. This is the window. Within the analysis, we will have operating conditions determination and also sensitivities analysis. This is the nodal analysis mode. We will determine the operating point. We can also find the pressure drop. But in this video, we will concentrate on the operating point. For the depth format, we can select either true vertical depth or measured depth. All right, this is the most important data input, calculation nodes. For our configuration, the top node, outlet node, should be our wellhead. So the pressure here is our wellhead pressure. In my case, I input 165 psia with temperature, wellhead temperature 80 degrees. The bottom node, of course, the inflow coming from the reservoir. So the node name will be reservoir at depth of 12,000. And the solution node, of course, our bottom hole. So the node name, of course, the casing 2. So the inflow coming from the bottom node, which is reservoir, and the solution will be at our bottom hole. Now we click set range. Okay, we can select the rates to be generated or to be shown in the IPR. Okay, we can click either rates or percent of AOF. In my case, I prefer percent of AOF from 0% to 100%. 0% AOF to 100% AOF. AOF also the same with maximum flow rate. Steps 10, fill, right? 0 stock tank barrel per day, of course, 0% AOF. With 100% AOF will be this number, 690. Click OK. Click apply. Calculate. All right. This is the inflow outflow curves. All right. And also the results. The first section is our operating point. So the operating pressure will be 1,408 with a liquid rate of 622.6, right? This operating point here. Oil rate, you can see here, because we have inputted our water cut. This is the water rate, gas rate. This is the data for our water cut, 0.15 with the produced GOR. And this is the stable flow. Very interesting. This is the inflow. And this is the outflow generated using Hagedorn-Brown correlation. You can also click this one for data editor. All right. You can check each section. Okay. Wellbore equipment profile. All right. For the tubing pressure, this blue line. And then this is the temperature. This is the report. And then the logs. Okay. Typical. All right. Now we can also do sensitivity analysis. Click sensitivity analysis. We can do two sensitivity. All right. And we can do sensitivity for a lot of parameters. Right. In my case, I will do analysis for fracture permeability. We will compare 60,000 in our original case with 50,000. Okay, and then 30,000, 10,000, and only 5,000. At it will be located here, manage sensitivity. And then for the sensitivity 1, we select fracture permeability. Okay, calculate. Calculation completed. We will go to plot variables. All right, this is the analysis variable. We go to here, sensitivity variables. We block all these numbers. Okay. All right. So this is our inflow outflow curves for the sensitivity, which is fracture permeability. You can see the results here. All right, with the given or the calculated liquid rate, oil rate, water rate, and so on and so forth. So it's very, very interesting, right? Even with fracture permeability of 5,000, we can still flow. All right. You can see we will have cross sections for each IPR with the outflow curves. All right, that's all. So in this section or in this example, we have learned about well modeling for a horizontal oil well with multi-stage fracturing. So I hope you enjoyed the video. I hope the video is useful. Thank you so much for watching. Please don't forget to subscribe, like, and share to your friends. And see you again in the next WellFlow videos. Thank you.